we're going to see first that mm, one second. Okay. So today we'll start with the similar problem. What we uh, maximum non-consecutive sum of n elements. So these elements are given in an array. So I'll slightly change this notation to highlight that this is the problem that we solved. This is nothing but what we solved last time, maximum non-consecutive sum n. So this was the notation that I used there, right? But I'm slightly changing this notation to highlight that the elements were given in an array, right? So I will now try to solve the same problem, but this time I will take them not in an array. Rather than that, I'll take those elements in a circular list. So input same as earlier, but they are given not in an array, given in a circular list. Right? And output is the same as before. Like I'm not writing. So what is the difference? Earlier, in this case of an array, the elements were like this. What are the consecutive elements? AI and AI plus 1. Those are the consecutive elements. But we have those consecutive elements also. But this time, since this is a circular list, now AN and A1, they also becomes consecutive elements. Okay, you understand the difference of these two problems? Is the difference between these two problems clear? So in the first problem, so in when the numbers are given in an array, right? You can have a solution which contains A1 and AN both. Okay? But you cannot have a solution if I give you the numbers in a circular list where it contains A1 and AN both. Right? So because A1 and AN becomes consecutive elements. Okay. So how do you solve this problem? Right, so you definitely understand that these are not the same problem. I have changed it slightly, but yes, so the approach will be again the same. So I will try to figure out how does the solution of maximum non-consecutive sum circular list, how does this look like? Again, so let S be a solution of this problem, right? So again, I can condition on this A. So there are two cases possible as before. Case one, the last element does not belong to the solution, right? So the solutions of this problem will be what? So what can I say about the solution? So in this case, what can I say about S? S is a solution of, can you tell me the problem for which S is the solution? Is it the S is the solution of Mn Cs Cl n minus 1? Is it? Okay, so since you don't understand, so I'll explain it. So An, I'm assuming that An is not in the solution. That says like S is basically a subset of A1, A2, An minus 1. Right? These elements are there. Right? But see, now in this case, A1 and An minus 1, they are not consecutive. But all the others are consecutive. Other pairs are consecutive. Right? So I can say that this will be again a solution of maximum non-consecutive sum of A1, A2, An minus 1. But I can here assume that these elements are given in an array itself rather than a circular list. So this will be a solution of the maximum non-consecutive sum of n A1 to A1 to An minus 1, and the elements are given in an array. Right? And what's the other case? The element An is in the solution. So what does that mean? So this will imply that I cannot have uh, A1 as well as An minus 1 in my solution. Right? I cannot have A1 to N minus 1 in my solution. So what would that solution look like? So S, so if I consider S minus An, this is now a subset of A2, A3, all the way up to An minus 2. Right? And still I can now A2 and An minus 2, they are not consecutive in the original input. So I can say that S minus An is a solution of the array version of this problem. When we have n minus 3 elements, okay, right? And these elements are basically A2 to An minus 2. These are the elements. Right? So basically what you're saying here is that it's a solution of another problem. So and now to solve this problem, so what we know that now to solve this problem, I need to know either the solution or not either, both the solutions of this problem and the solution of this problem, right? That tells you that while solving, and how do you solve this? That we have seen beforehand, right? In the previous class itself. I know how to solve this and this and the same similar problem with the same recursion like I should use. This highlights one fact that the original problem that you are solving, this is the original problem that you are solving. That original problem may not occur as a special case of the subproblems that you are solving. In the original version, the numbers are given in a circular list. But in the subproblems, the numbers are becoming such that I can assume that uh, they belong to an array, right? These are not the same type of problem. Okay. So to get the answer to this, I need to know the solution of this, and I have to do something, some amount of work I have to do to get the solution. So I'll be rewriting the main principles behind the dynamic programmings of dynamic programming. So what's the first step that you have to follow? Step one is identifying the subproblem. I need to first the subproblems and also count their numbers. How many subproblems are there? Let's say those numbers are fn. And then in step two, I need to analyze the solution. Analyze the solution to get the recurrence solution. To get the recurrence solution. Okay. And also, I have to, at the same time, I will also find the time per subproblem. Right? This is obviously without the recursive call. And suppose this is my g of n. Right. So in the last class, so what we said that the running time of this algorithm will be fn times gn. Right. But now we have just seen that I might have to, for some problem, I might have to do something extra to get the solution of the original problem. So that I'll write as step 3 here. Find the solution from the solutions of all the subproblems. This find the solution of the original. And suppose this takes h of n time. So the total running time of this dynamic programming approach this would be fn times gn plus the extra amount of work that I am doing to get the solution of the original problem. Right? Okay. Is this clear? Okay. So Having done this, so we now move to one of the most important problem that I'll call it's a knapsack problem. Or okay, let me state the problem first, and then we'll see how to solve this. Okay. So what is the input to this problem? So I'll be given some items along with their values. So I've given n items. So let's say I1, I2, In. These are the items that are given along with their values. These these are having some, each item is having some value and their sizes. Some specific size is also there. S1, each of these items are having this size. So item I is having value Vi and its size is Si. And you're also given a knapsack with a capacity of, let's say, capital C. So what is the question? So I have given you n items. Each of these items is having some value and this has a specific size. And I have also given you some knapsack, right, which has capacity C. Right? Capacity C means it cannot hold items whose sizes are more than, total size is more than C. Okay. Now, what I have to do, I have to figure out, uh, so I'll take this items as just 1, 2, 3, 4. Item 1, item 2, just for sake of easy. Now, what is the problem? Problem is that I want you to store as much as you can in the knapsack so that whatever you have taken in your knapsack, the total value becomes the maximum. Obviously, you cannot take all the items. I mean, in some cases, so if some of all these SIs are more than C, then you obviously cannot take all the items. So you have to throw away some items. So I want you to maximize the total value of the knapsack. How do I define the value of the knapsack? The items that you have chosen, you add the value of all those items. That will be the value of the knapsack. I want you to maximize the value of the knapsack subject to the constraint that the knapsack capacity cannot be more than. Have you understood this? Let me write it as well. What's the output? Input is a subset. I say S, which is a subset of these items. I have to take few items, right? with the maximum possible value. Of I belongs to S. Sum of all bi, but I belongs to S with the condition. Subject to the condition that what should be the condition? If I add the sizes of these items, that should not be more than the capacity of the knapsack. Okay. Is this problem statement clear? Okay. Now, let's say, for example, I give you an instance of this problem. Let's say I have these items. These are having some values, and I also need their sizes. Okay. So items are 1, 2, 3, 4. What are the values? Let's say 3, 2, 4, 4. Okay. And the sizes are 4, 3. Okay. And the capacity of the knapsack is given to be, let's say, 6. Now, I want you to pick uh, some item whose value will be maximum. Can you tell me which items should I pick for this example? So, okay, so item 4. Only item 4, or see uh, the answer should be a subset of those items. So if I take only the item 4, if I only take this item, then what is the value? Value is 4. And obviously I am within this capacity. So capacity, knapsack capacity is 6. The size of this item is 3. That's okay. Uh, Anything else? So item 2. So you're saying I take item 2 and item 4, both. That means this one and this one. So what would be the total size of these two items? Where does C equal to 6 come from? It's given. Okay. This capital C, capacity of this C is given. Right? As I said here, it's an input. So, yeah, so if I take these two items, then the total value is 6, right? And the total size is also 6. We are within this capacity. That's okay. But is it the maximum value that we can take possibly? Keeping ourselves within this. Or we may have item 1 and 3. Okay. So if I take item 1 and 3, so then I have sizes 4 and 2. Total size is within 6. That's okay. Okay. So the value will be 3 and 4. Okay. Correct. So now the value, so earlier value was 7. So earlier value was 6. Now we have, I can take, if I take these two items, so the value of the knapsack becomes 7. It's greater than that. Okay, so what you're saying here, we have 1 and 4 items of maximum C. So you want to take 1 and 4. Like, can you take 1 and 4? Their sizes are 4 and 3. So total size becomes 7, which is more than the capacity. Those I cannot take. Okay. So it looks like the maximum that we can possibly store in my knapsack is of value 7. Or can you see any other set of items which gives you a maximum value even more than 7? Yes, 4 plus 4, right? So its optimal solution will be taking 3 and 4, right? In that case, my sum will be 4 plus 4, 8. 4 plus 4, 8, right? But what's the capacity? Capacity is 2 plus 3, 5, right? That's okay. That is within the capacity limit, right? But that actually maximizes the total value of the knapsack, right? So it's not always that you have to take. So there are still some items like there are still some residual capacity. It's 6 minus 5. My knapsack is not completely full yet, but it doesn't matter. Still, I have the maximum value. Don't try to completely full your knapsack. Try to think in terms of which items gives you the maximum value. Okay. So the solution for this one, we can by observation. We haven't proved anything. Observation it says that the items that I have to take, item 3 and item 4, right? So the sizes are within the capacity limit and it gives you the maximum value is 8. Value of that knapsack. Okay. So let's say now uh, I want to know the recurrence relation for this. Right? For this means like the maximum value that you can, right? So for this, let me denote by this B, I, and C. Let this denote the maximum total value of a subset of first I items with total size at most C. Note that this C is I'm writing a small c. Okay. So what I'm saying here, the items are now you can think those items are 1 to I. Okay. And the knapsack capacity. And once I tell you these items are like this, their values are V1, V2, Vi, and sizes are S1, S2, Si. Right? And what's the capacity of the knapsack? Uh, what's the knapsack capacity? I'm taking here to be small c. Okay. I'm treating this one as my subproblem. I want to figure out how can I solve this problem using even smaller subproblems. Okay. So when I have items 1 to I and the knapsack capacity is C, VIC, this is the solution that I can, this is the maximum value that I can have. Okay. This is in fact a solution of that problem. Is this clear? Now again, what was the first step? We are going to analyze the solution. Right. So what's the first observation? So observation is that VIC um, may or may not have VI in it. I have not added the value VI to it, or basically the I does not, that is item I, the last item here, the item I is not included. Sorry, I should not say. um, Item I may or may not be included in the solution. Right, really two cases possible. The last item can be in the solution or may not be in the solution. So these are the basically two cases. Case one. So let's handle the easier one. Easier one first. Right? Item I does not not in the solution. Is not in the solution. It is like here I'm taking the solution to be yes. Okay. The item ith item is not in the solution. So what are the items that can be in the solution? So the solution contains items from which say what are the items that these can contain? I1 to I minus 1. Okay. And out of this is the maximum that you can have. Right? So I can say S is the optimal solution of the subproblem consisting of first I minus 1 items and knapsack capacity to be C. Okay. So basically, what is the solution for that problem? V I minus 1 C. That's the value that it can have. That's the solution. Okay. That's one case. And what is the other case? Case 2 is basically saying that uh, item I belongs to the solution. Okay. So it's there in the solution. So if I remove this I, S minus I, this contains, again, I can say the same thing. This contains items from 1 to I minus 1. This is still true. Right? Ith item in the solution. The remaining items are coming from 1 to I minus 1. But what is the capacity there? So I have taken the ith item. So now the knapsack capacity should be reduced. The size of ith item that should be taken out of the remaining the knapsack capacity. That will give you the remaining knapsack capacity. Right? So I can say that S minus I is an optimal solution to the subproblem consisting of first I minus 1 items, right? And the knapsack capacity that should be C minus SL. Do you follow this? Now, what is the case? What would be the solution for this value of this? C minus SL. Note that, let me, so this is possible, this case is possible. I belongs to S. This case is possible only if the size of that item is less than this C. Suppose the size of this SI is more than the knapsack capacity. So obviously you cannot take that item. Right? So this actually tells you how to find the solution of the problem where you have first I items, where you have this first I items and the knapsack capacity is C. So this value depends on this value and this value. It will be either of them. So this actually this plus this VI, right? Value of the ith item you have to add. So what is the recurrence that I can write? VIC. This I can write as, I'll basically break it into two cases. SI when SI is more than C. Right? So there's no possibility that the ith item belongs to the solution. This is actually small c. So what would be the case? Ith item in this case, if we have the size of the ith item is more than the capacity of the knapsack, so ith item can never be a part of the solution. So I have to take the first I minus 1 items, and my knapsack capacity will still be that. But in the other case, I will have two options. If I have Si is at most C, then the ith item may or may not be in the solution. Right? So in that case, I'll be looking into the solution of first I minus 1 item with a capacity C. That is what is the maximum value that we can have without taking the ith item. And if I take the ith item, so I'll have this value Vi. And with that, I have to take other items, but then the capacity of the knapsack will be this much, right? And it will be maximum of these two quantities. Okay. This is the recurrence that I'll get. Okay. So any question with this? It's fine. Any question? Okay. So I have this recurrence relation. So can you tell me what are the what would be the base case? Base case we can think of when we do not have any items with. So if V 0 C, this will be 0 for all values of C. And what are the values that this C can take? It can take any value between 1 to capital C. This I can take as base case. So how many subproblems? So before writing the pseudocode of the knapsack problem, I can tell you what is the running time of that. What is the running time of this problem? So to understand the running time, what do I have to know? How many subproblems are there? It's number of subproblems times what? Times the time per subproblem. Without the regression curve. Without the regression. Can you tell me how many subproblems do I have? This is true for C varying from 0 to capital C, and I is varying from 0 to, at max I can have n items. Okay. So number of subproblems are n times C. Okay. And The time taken per sub problem, what we are doing in this recursion. So we have some addition here and a comparison between these two quantities. Right? If you think these are the recursive calls, right? So that I should not be counting in here. So as I said, without the recursive call, what's the amount what's the time we're spending there? Without that, it's just a constant time you're spending. So what's the running time going to be? O of n. Okay. Note that this is not a polynomial time algorithm. Can anyone tell me why this is not a polynomial time algorithm? This is because that input size for this problem is n plus something else, n plus log of capital C. Right? The number of bits that I need to store the value of C. Right? That is the uh, input size. And in terms of that input size, this is no longer a polynomial. So in running time, we always express the number of primitive operations in terms of the input size. So in terms of the input size, this is not polynomial. Okay. Any questions so far? Okay. So now I'll write the pseudocode for this knapsack. So first, I'll initialize this memorization table. Let me name that table A. And what's the size of this table? It's n plus 1 times capital C plus 1. This is the size of this. I'll handle the base case first. So base case is these for every value of C, V0C will be 0. Right? For C0 to capital C, A 0 C, this is 0. This is for the base case. Right? And now what I do, I'm this is the actually this is the so I'm straight away writing the bottom up dynamic programming here. So I'll take for I equal to 1 to n and for C equal to 0 to capital C. If so, I'll just write this recurrence relation that we have here. If I have this condition, then this is nothing but this. If Si is greater than C, then what would happen? Ith item size of the ith item is more than C. So what would be the value that I should be having in here? That's the previous value of this I minus 1 C. Right? Else what will do? Else this value will be maximum of two quantities. I sorry, IC this is equal to maximum of A I minus 1 C and another quantity. That's ai minus 1, c minus si plus the value of vi. It's going to be the maximum of this quantity. Where is this coming from? This is just the recurrence. I'm writing this recurrence relation there. Okay. So straight away, you can see that we have two nested for loops, and the running time of this one is O of n. O of n capitals, not n square. So the I is going from 1 to n, but C is going from 0 to capital C, right? So it's n times capital C, not n square. Okay, right? So let me now illustrate this example that I had taken. This particular example, for this input, let me just now fill the table for me. Let me just resize it. Uh, what is the dimension of this table? The A, like the A is a two-dimensional array, right? So what's the dimension of this? And it's something, it's I and C. I will vary in this way: 1, 0, 1, 2, 3, 4. I have 4 items with me, right? And I have uh, C, capital C is 6. So I'll be having 1, 0, 1, 2, 3, 4, 5, 6. I have to basically fill this table actually. Right? So what is the base case? Base case is this one when I is 0. I is 0 means this first column. So I know all these values here. Right? I is 0. I know the first column. Now, how can I figure out this? So what is the uh, uh, next value that I'm going to get? It's actually first I'll get this value, then I'll get this value, then I'll get this value, this. In this way, I have written the following. For I runs from 1 to n and C is from 0 to C. So when I have, so what does this tell you? I have only one item. I have only this with me, right? And but the capacity of the knapsack is 0. Then what would be the value? So as long as the capacity of the knapsack is 0, I can straight away actually tell that maximum value that I can take is 0. Yes, this is clear. Now let's think about this. So I have only one item with me. I let me Now fill this column, the second column. I have only one item and knapsack capacity is 1. Can I take that item? I have the first item. The knapsack capacity is 1. Can I take that item? No, right? So because its size is 4. So as long as this, so the value will be 0. When the capacity is 2, still I cannot take that item. When the capacity is 3, still I cannot take this item. But when the capacity is 4, I can take the item, right? So what is the value then? Value of this particular item, value of this item. This will be 3 here. And any value above this, still I can take that item with me. Okay. Right. Okay. When I have now, I'll fill. So this column is done now. I'm now going to fill this third column. So I have two items. Right? I have two items with me. Can I take this item here? Can I? So when the capacity is 1, can I pick any of the first two items? No, because the size of first item is 4, size of second item is 3. So I'll be taking. So I cannot take when the capacity is 1, right? So this has to be 0. When the capacity is 2, can we take any item? No, still no. But when the capacity is 3, I can take actually the second item. And what's the value of the second item? It's 2. Right? Now, when the capacity is 4, then what would happen? So think about this case when the capacity is 4. So I have two options. Either I can take out of these two items, I can take the last one in the solution, or last one may not be in the solution. So actually it happens that the last one, when the capacity is 4, it's better to take the first item. And that will give me the capacity to be something like this. 3. So capacity is 4. I can use the whole knapsack and the value can be 3. Now, if I increase the capacity till 5, knapsack capacity till 5, then is there any possibility that I can take both of these values, both of these items, 1 and 2? No, because total size is 7, right? Which is beyond the knapsack capacity. So maximum that I can take is 3 of this, right? So like this, in this way, you can fill up this table. Okay. So let me just uh, do it quickly. Uh, so if capacity is 1, so always this is going to be 0. If I have always capacity is 2, then I can only take the third item whose value is 4. Right? If the capacity is 3, then I can take, yes, still that's the 4 is the maximum that I can take, right? 4 is the maximum that I can take. As in the capacity is 4. Right? I cannot take two items. So into 4 is this will still be 4. Now here's the interesting thing. Okay, this case is interesting. So what is this value? So in here, I have how many items? Items 1, 2, 3. These items I have, right? And the capacity of the knapsack, I'm assuming to be 5. Right? So there are two possibilities actually. So what is the size of the last item? Last item size is 2. The size of this item is 2. So there are two possibilities basically. This last item can be in the solution or may not be in the solution. Right? If suppose this last item is not in the solution, right? So what will be this? Yes, and so someone correctly figured it out. This is going to be 6. But my question is, how do you get that 6? Is it containing the last item or not containing the last item? Last item means like the item. So if it does not contain the last item, then what is the maximum value that I can take? That's going to be, so if I see this table, the size of SI is more than, sorry, is less than the capacity. So I am actually in this else case, right? So here, no, it's not going to be 4. So we are in this else case. So what do I have to check? I have to check what is the value to get to this value. What is the previous value in the previous column, right? And I have to check in that particular column when I have only 2 items, but I have to check something with the remaining capacity, right? With this one, so what does this tell you? This tells you that I have selected the item 2 here, right? And with this, if I add the value of the last item, the value of the last item is 4, right? So I have to take the maximum between 3 and this 2 plus 4, right? So this quantity is 3, this quantity is 2, and plus VI is 4. Right? So out of this, I am going to take the maximum. Right? So this is going to be 6. Everyone follows this? Now, can you tell me what is this value? This value. So how can I get this value? This value is maximum of what? If I think about this cell, the value in this cell depends on what? Depends on the case where whether this SI, what is SI here? I have 4 items with me. So S4 and the capacity is what is S4? S4 is 3 and the capacity of the knapsack is in this case 5, right? S4 is less than 5. So we are in this case, right? The value of IC, right? This value depends on this value I minus 1C, which is 6 in here, right? And what is this I minus 1? That will then, that is like column 3, And what is C minus SI? C is 5, SI is 3. So 2. I have to look into this column. This value is 4. And what is the value of the fourth item? Value of the fourth item is this one is 4. Value of the fourth item is 4. Yeah. Right? So this is going to be 6, maximum of 6 and 4 plus 4. That's 8. So do you follow how we're getting this? We are actually this going through the loop, this for loop here. And first I have to understand which case are we in and what is that. So again, just to get you familiar, what is this value? How do you get this value? This is 3A, like this. 3 items I have and capacity is 6. S3 to S3 here. What is the size of the third item? Is 2. Capacity here is 6. So then again, we fall in the second case, right? So value here depends on this value, the value in the previous cell. This one is 3, right? What is this value? The previous column and C minus SI. What is C minus SI? That is 4. I have to take this value. This plus what? This value is 3 plus the value of the third item. What is the value of the third item? This value is third item value here. Third item value is 4. Right? This plus a 4. Right? So maximum of 3 and 3 plus 4. Okay. So now I think it's okay to have this. And if you see, like, this is again going to be 8. Right? Okay. Actually, now once you know this value, once you know, so you want me to repeat the else case? Else case is what? Else case is something like this. When the size of the last item, right? So for example, we are figuring out this value. I'm trying to get, I don't know whether it's 7 or not. I'm trying to figuring out this value. What is the last the last item in this case is the third item. What is the size of the third item? 2. And capacity, what's the allowed capacity of the knapsack? It's 6 because we are in the 6th row, right? Okay. Now, how do you get it? So it's what is the else case? Else case is SI is less than the capacity. That is the else case here, right? So we are in here. Right? That tells you AIC depends on I minus 1C and I minus 1C minus SI. Right? This value, so we are checking this value, right? This value, this is AIC depends on I minus 1C. That is this value, which is there, right? What is AI minus 1C? It's 3. It's actually this particular cell, right? And what is I minus 1 C minus SI? C is 6, SI in this case is 2. So that is C minus SI is 4. Okay? So what is AI minus 1 and then 4? It's actually this value. This value is 3. And what is the value of VI? Value of the third item? Value of the third item is in this table, you have 4. So it's 4. So basically, you are taking maximum of 3 and 3 plus 4. Right? 7. That's how you're getting. Okay. Now this something else. So these are actually gives you, this table gives you the maximum value when these items are uh, given and there you go through this process. This table entries in this table are giving you the maximum value that you can achieve for your knapsack. 2 4 becomes 4. Are you asking about this one? Oh, okay. So let's see again. So item is I have 4 items in here. What is S4? S4 here. 3. What is the capacity here? What is the capacity of the knapsack? 2. In this case, can I take the 4th item? Size of the 4th item is 3, but the capacity of the knapsack at this point, you are not allowed to have. So I cannot take this 4th item there. Right? So we will be falling in this case. So that's why this value is coming from this value. This is 4A in according to our case. This is A42 that is coming from A32. It's clear now? Okay. So now if you look at this table, then you will realize that this value here is the thing that we actually want. Now this value is coming from not from this thing. It's actually coming from capacity 3 like this, coming from this value. So with this, you add the 4th item, then you get that one. So that says you have this 4th item with you. You have taken this 4th item. To get to the value of 8, you have this 4th item and you actually, so how do you get this 4 in here? How do you get this 4 in here? This 4 is actually coming from, I think it's from this one, right? It's not coming from here. It's coming from this, right? So it's basically this plus. So you are taking the 3rd item, right? So that actually, once you have this table, if you do this type of backtracking, then you can actually figure out which items that you are going to pick to have the maximum value of 8 in shape. So items that we are going to pick is 3M. Okay. Have you understood this? Any questions? Okay. So if there's no question, then should we conclude now? Okay, fine. So let's stop here. Thank you, everyone.